So with the second half of Chapter 5, we're going to look at uniform circular motion. As an object moves around a circle, its direction is constantly changing, so its velocity is constantly changing. So when an object is moving in a circle, it's constantly accelerating. So this is kind of a hard concept to grasp. So let's try looking at a picture to help describe the concept a little bit better. So centripetal acceleration is the acceleration that's occurring whenever you're moving around a curve or in a circle. So in the picture shown, there's a car moving around this half circle here. And the centripetal acceleration is this yellow arrow that is pointing toward the center of the circle. Okay, so that is why centripetal acceleration, centripetal meaning center seeking, because that acceleration is pointing towards the center of rotation, the center of that circle. So we always have centripetal acceleration anytime we're going around a curve or in a circle, anything like that, any type of rotational motion. To solve for centripetal acceleration, we have a different equation than we do for linear acceleration. So with linear acceleration, we used velocity and time to figure it out. With centripetal acceleration, we're using velocity still, but we're using the radius of the circle as well. So our equation is AC, C for centripetal, is equal to V squared divided by R. So we need to know the velocity of the vehicle, this green vector here, as well as the radius of the circle. And the radius of the circle is going to be in meters, so it's very similar to the distance, the d values we've been using in the Chapter 4 equations. Okay, the same units. With centripetal acceleration, we are talking about force in Chapter 5, so we're also going to talk about centripetal force. So centripetal force, therefore, is the center-seeking force, just like centripetal acceleration was the center-seeking acceleration. So centripetal force exists whenever an object is moving on a turn, just like centripetal acceleration. So it's a pull on the body toward the center of the circle. This is needed. Centripetal force is needed and always present in order to make something go in a circle. The centripetal force equation is going to be F sub C. So now we have three different force equations. We have just regular F equals ma, that's the linear force. We have F sub W is equal to mg, that's the weight force. And now we have F sub C for centripetal. So that's mv squared divided by r. So it's essentially mass times acceleration, because remember on the previous slide, v squared divided by r was what acceleration was, centripetal acceleration. So we're still taking mass times acceleration to figure it out, just like with the other two equations. It's just this time we need the centripetal acceleration to solve. So there are some pictures here showing centripetal force. So centripetal force is pointing towards the center of the circle, just like centripetal acceleration was. When you're doing these calculations, the mass is still going to be in kilograms, just like all the other physics problems we've been doing thus far. The velocity is going to be in meters per second, so no change there. And r, the radius of the turn, that's going to be in meters. I realize it's not on this slide, so let me just try to write an M there. So same units as other distances we've used thus far. With centripetal force, we also need to talk about centrifugal force. And what centrifugal force is, it's a felt force. So centrifugal force is not a real force. This is the force you feel due to inertia. Okay, so we talked about this a little bit with Newton's first law of motion. So what inertia is your body's ability or an object's ability to resist any change. So an example of this would be, say you're in a car, you're driving in a straight line. you all of a sudden need to take a sharp right. So since you're turning to the right, you're turning part of a circle. Any sort of turn, you need a centripetal force in order to complete it. So say you're in the car, you're going straight, you're turning to the right. What happens when you turn to the right? Where does your body go? Your body goes against the car door, right? To the left. It goes the opposite direction that the car is turning. The reason for this is because your body was going in a straight line. Okay, and your body has a certain amount of inertia, and that inertia is a resistance to any change. So if your body's going in a straight line, when you turn the car, your body's resisting that change. It doesn't want to turn. It wants to keep going straight. So you feel like you're slamming into the door to the left because your body's inertia is trying to continue straight while the car is trying to move you to the right. Similar thing happens when you're on a bus. Say you're standing up on a bus and you're holding onto the rail. Okay, you're stopped. You're not moving. Once the bus starts moving forward, what direction do you go? You usually fall backwards, right? So you're stopped, your body's not moving. When the bus moves forward, the reason you go backwards is because your body's inertia is resisting any change. It wants to stay motionless. So in reaction to the bus moving forward, it makes your body go the opposite direction, backwards. So this is the centrifugal force. This is the force you feel because of other forces, because of your inertia. Here's a depiction that I just described a moment ago. So if you are driving in a circle, the centripetal force is going, in this case, to the right towards the center of the circle. The centrifugal force, what you feel on your body, you go towards the car door in the opposite direction. So some other components of centripetal force. So we're back to looking at that center-seeking force, the force required in order to go in circular motion. So in order to go in circular motion, you need one of these other three forces there as well. We have force of friction, force of gravity, and the tension force. So let's look at each of these a little more closely, some examples. So with the force of friction, a good example is when you're driving a car. We just looked at it a moment ago, and you have to turn, right? Well, you can't turn without friction, and that is the friction of your tires on the roadway. So if it's icy out, or if it's been raining and it's a little slick, that means there's less friction on the roads. When there's no friction on the roads, you can't make that turn. You're going to keep sliding in the original direction you were going. So in order for centripetal force to occur, in order for you to make that turn, you need the force of friction, your wheels on the road, to make that happen. Force of gravity, so much larger scale, right? So in order for the moon to orbit Earth, it needs a gravitational pull on that Earth. Okay, so this is circular motion as well. In order for this circular motion to occur, in order for the moon to orbit Earth, there needs to be a gravitational pull. It's the same reason that the Earth rotates around the sun, is because of the sun's gravitational pull. We wouldn't be circling the Earth, having a centripetal force, circular motion, if it wasn't for that force of gravity. So these are our equal and opposite forces that Newton's third law described. And the last one, for centripetal force to occur, we need an equal and opposite force, that being the force of tension. Okay, so this is a smaller scale, obviously. So if you've ever taken a bucket full of water, if you can swing it in a circle fast enough, what happens is the water actually stays in the bucket. Okay, and that's because of this force of tension. In order to go in a circle, you need to have a certain amount of tension. So if you have a ball on a string and you want to whip that string around in circles, like a helicopter, say above your head, right? You want to whip that ball in circles. In order to do that, the string needs to be tight. It needs to be taut. Because if it's not, it's just going to bounce around all randomly. It needs to have tension in order for that circular motion to occur. Here are some centripetal force calculations that we're going to be looking at. So there's a video accompanying this PowerPoints with me working through these same examples. So take a look at that. Once you watch those, try doing some of the problems on the practice questions, the practice homework. Newton's universal law of gravitation. Definition of this is every particle in the universe is attracted to every other particle with a force joining them. What that means is there are forces everywhere, right? We've already seen that, but the forces due to the law of gravitation, these forces are very, very tiny. Okay, so these are forces. There's a force between me and the computer I'm looking at right now. Okay, there's a force between you and every object that's around you, whether it be people, a pencil, a desk, a door, a dog, a cat. Okay, you are exerting a force on everything around you, and everything around you is exerting a force back on you. These forces are so small, though, that we can't even feel them. However, they're large enough that we can calculate them. Because of gravity, you are being pulled toward your book, your pencil, every object around you, and everything around you is being attracted to you. This attractive force is called gravity. Now, Newton came up with this law of gravitational motion, and of course, since he came up with calculus, he also came up with an equation to calculate it. The equation to calculate is down below, F sub g. So it's a force calculation because it is a gravitational force. So that's what that sub g means, is gravitational force. Newton concluded that gravitational force is directly proportional. So remember, when we say proportional, that means if one goes up, the other goes up, to the mass of both objects. So if the mass goes up, the force goes up, is what that's saying. And it's inversely proportional. So inversely proportional meaning if one goes up, the other goes down, to distance. Okay, so we're going to look at this a little bit closer. These relations. So how did Newton discover this? His law of gravitation was discovered when he watched the apple fall from the tree. The force that pulled the apple to the ground was the same with which the apple was attracted to Earth. So watching that apple fall, he didn't just ask what caused it to fall. He said, well, the apple must be exerting a force on the Earth, just like the Earth is exerting a force on the apple. So that's what these minute forces are. So looking at the relationship between these forces in that equation, the gravitational force depends on two things: the mass of the objects and the distance between the objects. Okay, so we saw that from the equation briefly earlier because there were m's in the equation as well as a r, a radius for distance. So the force of gravity acts between all objects. We said that mass and force were proportional to each other. So if they're proportional to each other, that means if one goes up, the other goes up. So if mass increases, the force is going to increase. If mass decreases, the force is going to decrease. As for distance, we said that distance and force were inversely proportional. Inversely proportional means if one goes up, the other goes down. So if distance increases, goes up, that means force is going to go the opposite direction, down. It's going to decrease. Some examples of this. Earth attracts an elephant more than a cat. Okay, can you prove this? With that weight force, right? An elephant weighs more than a cat. So what that means, the higher the mass, the higher the force. An elephant has more mass, so mass goes up, force goes up, because mass and force are directly proportional. Mass goes down, so a cat, then the force is going to go down. Earth's gravitational force is more than that of the moon. What that means is Earth's gravitational force is higher, so that's why the moon orbits Earth rather than the other way around. So mass goes up, force goes up. So Earth has more mass, so it has more gravitational force, causing the moon to orbit around the Earth. Gravity between you and Earth is greater than gravity between you and the sun. So this is looking at how force and distance are related to each other. Remember, force and distance were inversely proportional. So you are closer to the Earth than you are to the sun, right? So the distance you are to Earth is really, really low. So distance is low, so down. Since distance and force are inversely proportional, that means the force that Earth applies to you is really great. So that's why you're on Earth, because you are close to it. Your radius is low, so the force is high. Now let's look at the equation and how we're going to use this to do some calculations. So F of G is the gravitational force. That's what the G stands for. It's between two objects, so that's why we have an M1 and an M sub 2. So mass of object 1, mass of object 2. So there's always going to be two masses in these word problems. Gravitational constant, this big capital G here, that is not something you are going to be given in the word problem. That is a constant that is going to be the same every time you use that equation. This constant is given to you on the equation sheet. The constant is 6.67 times 10 to the negative 11th. Remember, negative 11th, that means it's a very, very small number. That means we are taking this decimal point and we're moving it 11 times to the left. So very, very small. I'm not even going to move it that many times. That's why in the end, when we're done calculating these, F of G is actually a really small number due to that gravitational constant. Okay, these are very small forces. So M sub 1 is the mass of the first object. We are still using kilograms, so nothing changed there. So make sure both those masses are in kilograms before you plug them into the equation. The last variable, the R, that is the distance between the centers of masses of the two objects in question. We are still measuring it in meters, so that has not changed either. So make sure to keep checking your units, converting if necessary, and then plugging them into the equation. I will not ask you to rearrange this equation. Characteristics of gravitational force, just a quick review. Remember that with this equation, mass and force are directly proportional. So that's what this symbol here means. They're directly proportional. So if one goes up, the other goes up. One goes down, the other goes down. Distance and force, however, are inversely proportional. So if one goes up, the other goes down. So the further you are from something, higher the distance, the less force you are exerting on it. The lower distance, or the closer you are to something, the higher force you are exerting on it. Here are the two calculations that I will be working on the video. So take a look at those and then try some of the example problems on your own before taking the Chapter 5 quiz.